Hi class. In this chapter, chapter 16, we're going to talk about how stars are born. In the last two chapters, 14 and 15, we talked about our sun in particular and what's going on inside of our sun and how we know that, how we measure these things. And then in 15, we looked at just observing properties of stars throughout the universe. As we observe them, what do we observe? Do we observe different temperatures, masses, distances, luminosities? And so we try to look at a pattern or patterns that we could see between those variables. And we found that mass was a big determining factor in what happens to a star, in how the star lives its life, how long it lives, how hot it gets, how big it gets, and so on. In this chapter, we're going to talk about where are stars born and how are they born? How does gravity actually create a star in the first place? So star birth is the topic of this chapter. First part, we're going to look at what we call stellar nurseries, the places where stars are formed, and what is the evidence that we have that stars are being formed there, and why are they being formed? What causes them to be formed? So where do stars form? This picture here is a cloud of gas and dust. Clouds of gas and dust are called nebulae, plural, or nebula, singular, and these are more dense regions than what you would normally find between stars in the galaxy. So all the dust and the stuff between stars in a galaxy we call the interstellar medium, or ISM. And there's just gas and dust in there. There are some places where the gas and dust is thicker, more dense than other places, and those show up as clouds out in space. So this is a picture of a cloud, a dusty cloud out in space, and there's some stars near it, around it, different color stars, and so on. And we can look at the spectrum of the light from those stars that are maybe behind the cloud. So we've learned in previous chapters that when we look at the spectrum of light coming from a star, it's an absorption spectrum. And we can see evidence of gases, of atoms in the star's atmosphere that absorb certain wavelengths, certain colors of light. And by looking at the spectrum then and looking at what colors are absorbed, we can determine what the elements are, what the atoms are that make up the star's atmosphere. Well, if that starlight, though, passes through a cloud, so if I draw a little picture, if this is the Earth here, Earth, this is you, your telescope is here, you're looking at a star, here's a star over here, and you're looking at the light that comes off that star, so there's light that comes off the star coming toward the Earth. If there's nothing in space, you're just going to see the light coming from that star, and any absorption lines that you're going to see, any missing colors you're going to see, is because of stuff being absorbed by gases in the atmosphere of the star. But if there's a cloud of gas between us and that star, some cloud of gas, that light has to pass through this cloud to get to the Earth. And a couple things happen to the light. Some of the red light will just go straight through. This could be red. Some of the bluer light can actually get scattered away and kind of bounce in different directions, and we might not see as much blue light coming through the cloud from the star as we would normally see without the cloud. This is similar to why sunsets look more red than when the sun is higher up in the sky, because at sunset the sun is traveling, the sunlight is traveling through more atmosphere to get to your eyes than it does when it's higher overhead, and so the sun appears more red. So the more cloud, the more stuff, the more dust and gas that light has to travel through, the harder it is for the shorter wavelengths of light to get through. The longer wavelengths have an easier time. So red light has an easier time of getting through than blue. But a lot of the light of the star will get through, possibly, if the cloud is not very thick. And so some of the light can get scattered. Some of the light could get absorbed. If some of these colors are just the right energy, the light could get absorbed by atoms in the gas. And those atoms could then, they absorb that light, and then they could re-emit the same wavelength, the same color, same intensity, or same energy, but in some random direction. And so we just don't see it. So what we see when we look at this star is we see that a lot of the blue light might be missing, simply because it's getting scattered away. But amongst the other colors that we see, there might be gaps. There might be a very particular yellow color, for example, that is missing. There might be a very particular red color that's missing. And by looking at those very particular colors that are missing, we can identify what atoms are in the gas that's between the star and us. And we can also determine by looking at Doppler shifting of those colors that are missing. We can match these missing colors up and decide what the atoms are that they belong to. But if those colors are slightly shifted from where they should be, then we know that there's some Doppler effect going on, and the gas is actually moving around, and we can measure the temperature of the gas. in that way. That's actually one way we can do it. There's other ways as well. So the spectrum shows a bunch of absorption lines. So the light in this is a very narrow range of wavelengths, 126.0 to 126.2. Very narrow range of wavelengths. The brightness of the light is high, and then suddenly the brightness of the light goes way down. So there's a lot of absorption of these wavelengths in here. And that happens to be due to atoms like iron and silicon. And then there's other absorptions. There's a strong absorption right here, a very low intensity at this particular wavelength, and so on. A lot of these absorptions are due to carbon atoms. And so we can identify what's in these clouds by looking at the absorptions of certain colors in the spectrum of the light coming from a star that's behind the cloud. Ultimately, we find out by looking at a bunch of clouds of gas and dust that they contain about 70% hydrogen, about 28% helium, and about 2% heavier stuff. And by heavier stuff, we just mean anything bigger than helium. And that would include molecules as well as other atoms. So this picture is a picture of the Horsehead Nebula. And when we look at it in visible light, it looks pretty dark. It's very thick. Not a lot of light is getting through it. You can see some little openings in there, but it's very dark. But we can look at it in a different wavelength. We can look at it in a wavelength that is what carbon monoxide would emit. So again, all atoms and all molecules absorb and emit certain colors. It just so happens that carbon monoxide emits a particular wavelength of radio wave. It's about 21 centimeters in wavelength. And if we look at this cloud with a radio telescope using a detector, a camera of some sort that's sensitive to that 21 centimeter radio wave wavelength, we get another picture of the cloud. And so what we are seeing then is we're seeing areas in that cloud where there's a lot of carbon monoxide, because this color comes from carbon monoxide. So there's a lot of carbon monoxide in this cloud, and there's some areas that are more dense than other areas. So we can identify certain molecules in these clouds based on the colors that they emit. So we can look at both an emission spectrum, actual light coming from the cloud itself, or we can look at an absorption spectrum, looking at the light that's missing from a star that's behind the cloud, that light traveling through the cloud. Some of the colors get absorbed. So by analyzing clouds, looking at the carbon monoxide and other molecules that these clouds are made of, we find a few things. We find that these clouds have a very low temperature, somewhere between 10 and 30 Kelvin, so very, very close to absolute zero. They have a very low density, about 300 molecules in a cubic centimeter. So a sugar cube is about a cubic centimeter, 300 molecules in there, roughly, per cubic centimeter. Let's contrast that with what the density is of the air we breathe. The air we breathe has about 10 to the 19 molecules or atoms per cubic centimeter. So that's 1 followed by 19 zeros. That's a very big number compared to 300. So these clouds of gas and dust are very sparse, very diffuse. If you were to fly through one of these, you would hardly notice that you're in there at all. You would hardly notice that you're in this cloud. There would be less resistance to your motion than there is driving down the road right now in the air that we breathe. You would almost feel like you're just in empty space. But the reason why they look so thick is because they're incredibly big. They're several light years across, several light years deep. So they're very large. And when you're looking through a really large cloud of gas and dust, even if it's so diffuse, so spread out, not dense at all, it still looks dark, it still looks thick, but it isn't really. We can look at dust particles too, and what dust particles do. These are the guys that are responsible for scattering that blue light and the purple light, and it's these dust particles. And a similar thing happens in the air that we breathe. When we have dusty air, the sunsets look even more red, even deeper red. When there's a volcanic eruption, the sunsets look even deeper red. They look even more vivid. And that's because of the extra dust in the atmosphere. And it's that dust that causes the blue light and those shorter wavelengths to scatter away and allow mainly through the longer wavelengths like the red and the orange and so on. So these clouds of gas and dust also have these particles of dust in them. But this isn't ordinary dust like you and I think of in our house. In our house, a dust particle is more like dead skin cells. It's kind of gross, but it's true. But these dust particles are just atoms clumped together, some iron, silicon, carbon, oxygen, and there's no cells in here as far as we know. And so these are just chunks of atoms of small size. So this is about 1/10 of a micron across here. Not 1/10. This is maybe about 1 micron across, this whole thing. And if you think about a human hair is about 50 to 100 microns across. You could fit You could fit 50 to 100 of these across the width of your human hair. These are really tiny, tiny dust grains, much smaller than the dust that you normally think of in your house. But these are the things that we also find in the molecular clouds, and these are the things responsible for turning stars sort of reddish looking. If we look at this cloud of gas and dust, this is called Bernard 68, and it looks very dark and thick. You can hardly see anything in the center area. It looks like there's just a hole in the sky. And that's at first what people thought. There was just a region of space where there were just simply no stars. But it's a cloud of gas and dust. And the way we know this is because we can look at this object in different wavelengths. So this is a visible light photograph, and you can see stars around the outside of it, and you can see stars near the edge looking very red. That's just like a sunset. The blue light that these stars are giving off is being scattered away, and the main light that's coming through is more the red light. Well, what about infrared? If we look at this in the infrared part of the spectrum, we see a lot of stuff coming through. So we'll go back and forth between these two pictures. This is the infrared photograph, this is the visible photograph. In the longer wavelength photograph, we can actually see through the cloud, because the light coming from these stars in the center, for example, hardly any of the visible light is able to get through because the cloud is so thick in the center. But we can now see those stars if we look at the infrared light that they're giving off. That longer wavelength, much longer wavelength infrared light is able to get through these clouds. And so we can analyze the thickness of the clouds also by determining how what we call attenuated the light is from the star, how diminished it is. We can figure out the thickness of these clouds. At least that's one way of getting an approximation. So we look at clouds in many different wavelengths to determine what they're made of, how thick they are, and what's behind them. Here's another object, the Eagle Nebula, and it looks like an eagle if you look at it in the right way. You can try to figure that out. Where's the head of the eagle, where the claws of the eagle, and so on. But this is again a visible light photograph, and you can see stars on the outside of it, and you can see areas kind of in the cloud itself where there's some things glowing right there. We can look at this in the infrared part of the spectrum. It looks very different, and we can definitely see stars inside the cloud. And so these are like newborn stars, and you can see in here there's a star giving off a lot of infrared light. These are not lined up perfectly, these two images, but if you kind of go back and forth between them, you can kind of make out the stars that appear and disappear as you go from one to the other. And so we can see inside these clouds by looking at infrared light that newborn stars are emitting deep inside these clouds. Here's another image of what dust grains can do. Dust grains are not atoms, but they're clumps of atoms, and they can absorb energy as well. And just like things here on Earth, when you warm them up, they give off infrared light. So you and I are actually infrared light bulbs. Because we're at a certain temperature, we emit infrared light, and we can see each other if we had eyes that were sensitive to infrared light. We could turn all the lights off, have it completely dark in terms of the visible, but if our eyes were sensitive to infrared light, we would see each other still. So this picture down in the bottom is a visible light image, and you can see, it looks kind of dark in this area here, around here as well. It looks kind of dark, but if you look at this in the infrared part, it's glowing. This whole region here is glowing gas. It's not just a spot that's glowing like a single star, but it's a whole region that's glowing. And that suggests that there's a lot of dust in here that's being warmed up by something, like a newborn star inside the dust. So the dust is warming up the star is warming up the dust, and the dust is glowing in infrared light. It's emitting infrared light. So that is where we see stars being formed in these nurseries. But why do they form? Why do stars actually form? How does gravity make stars form or help stars form? So gravity ultimately takes this gas and dust and tries to squish it, tries to compress it. And you've learned from previous chapters when we talked about the evolution of our solar system that as gravity tries to squeeze a cloud, or if you drop an object from high above the ground or something, as the object falls, you get this conversion between gravitational potential energy and kinetic energy. In other words, as gravity pulls on something, it speeds up. And so in a cloud of gas and dust, as gravity's pulling on it, this cloud, squishing it together, everything is speeding up. And a higher speed implies higher temperature. So what we're doing is we're getting a conversion from gravitational potential energy to thermal energy, to higher temperature. There's a problem though, and that is that as the temperature goes up, there's this thermal pressure that pushes back. And so it becomes harder and harder and harder for gravity to overcome the thermal pressure in a cloud as it squeezes it. And so gravity can try as hard as it can to squeeze this cloud of gas smaller and smaller, and the temperature will continue to increase, but that thermal pressure will also increase, making it much harder for gravity to squeeze it any further. And so what we need to make a star is we need a very dense region that is very hot. And so if a cloud gets too hot too fast, then gravity might not be able to make it dense enough. So again, we need 2 protons. To start a nuclear fusion process, we need 2 protons. There's a proton moving this way, let's say, and here's a proton moving this way. We need 2 protons to come together at a high speed to be able to get close enough so that the strong nuclear force can make them stick together. Well, high temperature means, a really high temperature means that they can move fast enough to do that. But what are the chances that 2 of them are going to come directly and hit head on? The chances are much higher that that will happen if the gas is more dense. And so if gravity squeezes a cloud of gas, even though the temperature might get high enough, the speeds of these particles might be high enough, you still might not have nuclear fusion happening at a high enough rate to actually form a star because the density of the gas might not be high enough. So 2 things have to happen. The density of the gas has to be high enough and the temperature has to be high enough. So molecules come into play here. What molecules in these clouds do is they help absorb some of that thermal energy, and they turn that thermal energy into light, like the carbon monoxide giving off the 21 centimeter wavelength light. They turn that energy into light, and they help keep the cloud somewhat cool. It doesn't help make the cloud really cold, but it helps to keep the cloud from getting too hot too fast, so that gravity can continue to squeeze the cloud, can continue to make the density increase while the temperature increases at a rate, though, that will allow for significant nuclear fusion eventually. So molecules are very important. A typical cloud we had talked about before was about 30 Kelvin, and the density was about 300 particles per cubic centimeter. And so there must be enough gravity to squeeze the cloud to overcome this thermal pressure, even if you have these molecules helping you keep the cloud a little bit cool. So if you're going to form a 1 solar mass star, you don't just start off with a cloud of gas that is 1 solar mass. That cloud of gas might get broken into several pieces and form several stars. So really you might need a cloud of gas that's 10, 20, 30, 40, 50, maybe 100 times the mass of the sun to actually form some stars that are the same mass as our sun. So if we think about, we want to think about these molecules and why are they so important. Let's go back to atoms just to remind ourselves about some things. Atoms absorb energy. And if you imagine having 2 atoms colliding, so here's an atom, here's an atom. These are not, just protons. Maybe they're just hydrogen atoms or whatever atom. So if these 2 guys come together at a certain speed, they can bump into each other. As they bump into each other, if they have enough energy of motion, enough kinetic energy, it's possible that some of that energy of motion could go into one of the atoms, causing it to increase its energy from the lowest energy state to one of the upper energy states. But remember, there are certain specific values of energy that you can have, otherwise the atom doesn't absorb anything. For hydrogen, there's a minimum amount of 10.2 electron volts. And that's true for all other atoms too. So atoms themselves require a minimum amount of energy available for them to absorb anything. So if these atoms are part of a cloud of gas that's fairly cool, when they bump into each other, there's just not enough energy there. They're just going to bounce off of each other and go on with the same total kinetic energy. Neither of the 2 atoms will change internally at all. Molecules, though, are different. A molecule you can think of as 2 atoms kind of connected by a little spring, sort of. As one molecule travels sort of toward another molecule or even toward another atom, if these 2 guys collide now, and let's say they're traveling at a slow speed, just like the atoms up here were, if these 2 guys come along and collide, the difference now is that these molecules have a kind of a richer sort of possibility of ways they can absorb energy. And they can absorb smaller amounts of energy than what atoms can absorb. So even if the cloud is fairly cool, as they come together at somewhat slow speeds, there might be enough energy there for them to absorb some of that energy. And then they do something, they might vibrate or wiggle around a little bit more, but then they might immediately release that energy. But what they've done is they have taken energy of motion and converted it into light energy by absorbing that energy, converting it into an internal sort of vibration or rotation, and then emitting that energy in the form of light. So molecules help convert thermal energy in a cloud, energy of motion of the atoms and molecules, into light energy, and they thereby help keep the cloud from getting too hot too fast, so that gravity can ultimately win, and gravity can ultimately form a star. If we look at a little simulation here, this is that website, Phet.colorado.edu. They have some good simulations here. Here I have a carbon monoxide molecule, and you can choose other molecules if you want to see what they do. But if I shine ultraviolet light on that carbon monoxide molecule, what will it do? Let's just see what it does. So let's turn on our little laser, shine some ultraviolet light on that carbon monoxide molecule, and all this is a carbon and an oxygen bonded together, and the little bond is almost like a spring holding them together. Well, nothing's happening because this energy of this ultraviolet light is too high. The carbon monoxide molecule only absorbs certain energies. So what about visible? Well, visible also is too high. Visible, it has less energy than ultraviolet, but it's still too much energy. The molecules, again, won't absorb that much energy. All right, atoms will certainly absorb some visible light and ultraviolet light. We've talked about hydrogen, the hydrogen atoms and the different colors that it absorbs and emits. But what about infrared? Let's go to lower energy. So infrared light, oh, look at that. We've got absorbed photons. So when light gets absorbed by this molecule, you see it vibrates more, and then it emits a photon off in some other random direction. And so if in the molecular clouds, instead of having light coming along hitting the molecule, imagine that this is a sort of a gun that's shooting other molecules or other atoms at this molecule. And if it's a low enough energy atom traveling along here and it hits the carbon monoxide molecule, that carbon monoxide molecule can absorb some of that energy of motion and vibrate a little bit and then turn that energy into light. And so ultimately it's converting energy of motion or thermal energy into light. And the cloud glows in the infrared part of the spectrum, and it radiates its energy away so that its temperature doesn't get too high too fast. We can also do microwave light, shine microwave light on there. And the microwave energy is even lower. But that can be absorbed by the molecule, but it causes the molecule to do something different. It causes it to rotate instead of vibrate. So there's certain rotational energies available to a molecule, and those are lower energies even still than the vibrational energies. So molecules can do a lot of different things. They can absorb a lot of different energies compared to atoms. So there's other things then that gravity has to resist. Gravity, the cloud of gas might also have magnetic fields in it, and it typically would because magnetic fields come from moving charged particles, and there's a lot of moving charged particles in these clouds. And so it's possible you could have magnetic fields, and the magnetic fields will tend to prevent the cloud from collapsing too fast. So gravity has to try to counteract magnetic fields as well. So if you have a cloud of gas and dust that's very turbulent and has magnetic fields in it, and it doesn't have a lot of molecules, it's going to be very difficult for gravity to contract that cloud enough. There would have to be enough mass there so that gravity was strong enough to make that cloud small enough or contract it tight enough to increase the temperature and the density to form a star. So again, gravity within a contracting cloud, gas cloud, becomes stronger as the gas becomes denser. And then gravity can, once it becomes strong enough, it can overcome the pressure in smaller pieces of the cloud, maybe not the entire cloud, but in smaller pieces of the cloud. And so typically the cloud will break up into small pieces, and you won't necessarily get one star out of your one initial cloud of gas and dust. You might get many stars out of that cloud. So we can look at this little simulation, and we'll run this. This is on your D2L site, and it's one of these interactive figures. So this is a movie, a computer simulation that started off with a ball of gas and dust that was about 1.2 light years across, and it's in the start of this movie. It's gonna just let the computer run, and the computer's just gonna kind of knows the laws of physics, and it knows what gravity is going to do, and it knows what the atoms and molecules are going to do. So it's about 1.2 light years across. So let's play this, And we'll see some yellow regions forming, and those are places where the density is becoming higher. So gravity is squeezing the cloud, but notice how it becomes fragmented. It doesn't just all squeeze together in one place. So this particular cloud of gas and dust, which is about 50 solar masses worth of stuff, is going to form many stars. And so as we watch this go here, it pauses every now and then. The densities in the cloud are now much larger than before. The scale is shifting towards greater number of higher density regions. So that the scale on the bottom is going to shift a little bit, just to kind of recolor things. And so now this area isn't as yellow as it was. It's recolored it a little bit. And now it's getting more yellow in here. Now the simulation will rotate and zoom in on this bright, really dense, over-dense region to see how the star cluster forms. And so we're going to rotate and zoom in a little bit. Again, this is just a computer simulation. There's a time up here. 197,000 years have gone by. In this simulation, 1 second of our time is about 1,000 years in the simulation's time. So we can see some things going on here. There's a lot of swirling. There goes some new stars flying off that are being formed. Very dense regions. So there's new stars being formed in all these really dense yellow regions here. So the small spiral is a cluster of stars forming. New stars are often expelled from the cluster due to gravitational interactions. And so things continue to spiral and interact and pull on each other. Gravity pulls in more material. Several overdensities in different parts of the cloud are now coalescing in the region we've been observing. More clouds are formed, or more stars are formed and ejected from the dense regions. And then it continues to go on, and you can see more stars being flung out through gravitational interactions, and other regions that are forming stars up here, and a lot of star formation in here. And then it'll pause here in a second. This region we were looking at starts to go down, and it's pulling in gas now from around it, making things even more dense, making even more stars. So the dense center of the new cluster has shifted position from our viewpoint due to the collisions of different overdense clumps, and still more dense gas is coalescing there. So gravity is pulling things in now. Once gravity gets strong enough, once the mass gets dense enough, then it can start pulling in more material, and the star formation process can continue to go on in that region. So we've got all these stars being flung around now, and everything's kind of rotating around, and ultimately we'll have this cluster of stars that are formed, all moving around some center of the cluster. So the region we're now observing has condensed so much that it is drawing gas from further regions. The central dense part of the cluster has formed. What remains of the gas may still be used to form stars, though less violently. And so we zoom back out, and now we see that whole ball of gas again has formed all kinds of stars way out in the perimeter, as well as a lot of dense regions in the center. So this will go on to form a nice cluster after a few more thousand years probably. So this has only been 266,000 years. That seems like a long time, but in the lifetime of a star, that's not very long at all. So these star formation processes seem to happen fairly quickly compared to how long a star lives. So again, the random motions of different sections cause the cloud to clump, and then each clump is a place where gravity can overcome pressure, and ultimately it can become a star. A large cloud can make a whole cluster of stars. If it's a smaller cloud, you could possibly get 1, maybe 2 stars formed in the cluster. It's possible. So what would happen to a contracting cloud fragment if it were not able to radiate away its thermal energy? So it couldn't get rid of that thermal energy. That thermal pressure couldn't be dissipated. So A isn't quite right. It would not continue contracting because, well, it says it would continue contracting, but its temperature would not change. That wouldn't happen. So if gravity squeezes a cloud and continues to contract it, temperature always goes up. There's always an increase in thermal energy because of the decrease in potential energy. B is not right. Its mass would increase. That's not going to happen. There's no additional mass coming into the cloud from somewhere else. So the answer is C. Its internal pressure would increase. And that internal pressure would increase and prevent gravity from further contracting the cloud. And ultimately it could prevent gravity from getting the cloud to be dense enough so that nuclear fusion can go on. So what about the very first stars that were formed? In the very beginning of the universe, all we had was hydrogen and helium, and maybe a little bit of lithium. We didn't have any carbon or oxygen or anything higher than lithium. And so we didn't have molecules, no carbon monoxide molecules. And so those carbon monoxide molecules weren't there to help cool the cloud. They weren't there to help keep the cloud from getting too hot too fast. So in order to form the first star, there must have been a lot more mass present so that the cloud could have a much stronger gravitational contraction. So if there were some really wimpy clouds out there in the early universe, they just wouldn't form clouds. They just would not form stars. It was the clouds of gas and dust, not even dust actually, there was no dust back then, because again, dust is carbon and silicon and iron and so on. It was just pure hydrogen and helium and a little bit of lithium. So if you had some low mass clouds out there, they just wouldn't form stars. They might get some areas that are dense and hot, but the temperature would be so high, the thermal pressure would be so high that gravity just couldn't squeeze it any further. But it wasn't these, you'd have to have really, really massive clouds of gas so that there was enough mass there to really be able to make gravity strong enough to overcome that intense thermal pressure, to be able to get the density high enough. And so these very large, massive clouds would have formed very large, massive stars. And those stars could have been about 100 times the mass of the sun, the very earliest stars. Right? So again, these very earliest stars had to have been more massive because they needed more mass to overcome those thermal pressures of the high temperatures of these clouds, because there was no mechanism for cooling them. And so gravity had to overcome that thermal pressure to be able to contract the cloud enough so that there was high chances of nuclear fusion happening. The temperatures might have been high enough for the protons to crash into each other and stick together and to have nuclear fusion, but if the density isn't high enough, it's just not going to happen very often. So you need a high density as well as high temperature, and the massive clouds back in the early universe would have had enough mass to squeeze the cloud hard enough to make it dense enough so that you could have an actual star forming. So the very first stars were very massive. And then those very first stars lived very short lifetimes, maybe 1 million years, maybe. And they formed all kinds of other atoms inside of them, like carbon, oxygen, magnesium, silicon, iron. And then when they exploded, they dispersed that material throughout the interstellar medium. And then the second generation of stars are formed from that. And that second generation of stars could be smaller stars then, because they would have had those atoms to form molecules inside of the clouds. And so they would have had molecules available to help the clouds cool, and so that would enable a smaller mass cloud to form a smaller mass star. So the first stars were very massive, but the second generation stars could be less massive. So in summary, in this section, we talked about where our stars formed. These stellar nurseries are just these molecular clouds, cool molecular clouds that are typically about 70% hydrogen, 28% helium, and about 2% other stuff. And that other stuff is everything other than hydrogen and helium. And then the clouds had to be massive enough so that gravity can overcome thermal pressure, and the molecules help with this process by keeping the cloud from getting too hot too fast. And then typically the clouds break up into pieces and form many stars instead of just a single star. So in the next section we'll look a little bit more closely at the birth of a star. And so this section was more about how do they form in general and where do they form. But now we'll look more specifically at the birth of a star.